Imagine it is 2 a.m. on a Tuesday and your phone starts buzzing. Your RAG-based search application is suddenly returning irrelevant results or timing out entirely. You check the logs and see a massive latency spike, but here is the kicker. Your primary database is healthy. The culprit is the synchronization worker between your Postgres instance and your specialized vector database. It has lagged by over 5 minutes. In a distributed architecture where your metadata lives in SQL and your embeddings live in a separate vector store, you are essentially managing a distributed transaction without a proper coordinator. When traffic peaks, the ETL pipeline that pushes embeddings from the source of truth to the vector index becomes the ultimate bottleneck. This results in the stale vector problem where users search for items that don't yet exist in the index. By the end of this lecture, you will realize why the 2026 architectural trend is moving aggressively toward consolidation to kill this nightmare once and for all. In the field, I often see teams struggle with the hidden costs of split architecture. You think you are gaining performance by using a specialized engine like Pinecone or Qdrant, but you are actually paying a massive tax in operational overhead. Every single write operation now requires a dual write strategy. If your primary DB commit succeeds, but the vector index update fails, your data integrity is gone. You have to write complex retree logic, dead letter queues, and reconciliation scripts just to keep things standing. Furthermore, when you perform a filtered search line vectors similar to X, but only for customers in region I, the system has to jump between two engines. This network hop alone can add 50 to 100 milliseconds of latency, which is unacceptable for modern real-time AI agents. This is the architectural debt that most developers ignore until it's too late. But wait, is there a way to eliminate this complexity without losing the speed? Let's look at the alternative that is taking over the industry. The landscape in 2026 has shifted dramatically. We are moving away from the fragmented stack and toward Postgres-centric AI. With the evolution of extensions like pgvector and specialized scaling layers, the performance gap that once justified separate vector databases has almost vanished for 90% of use cases. Why manage a separate cluster, separate security IAM roles, and separate billing when Postgres can handle 100 million vectors with sub-10 ms latency? The simplicity of having your relational data, JSON metadata, and vector embeddings in one single ACC-compliant engine is the ultimate competitive advantage for engineering teams who want to move fast. In this lecture, I will show you exactly where the tipping point lies and when you should and shouldn't abandon your specialized vector store. But isn't Postgres supposed to be slow for high-dimensional search? In the next chapter, we will look at the 2026 benchmarks that completely flip the script on performance expectations. By 2026, the long-standing myth that specialized vector databases are inherently faster than general-purpose ones has been completely dismantled. When we look at the high-scale benchmarks involving 50 million vectors, the data is undeniable. pgvectorscale, the performance-focused extension for PostgreSQL, delivers a staggering 471 queries per second. Compare this to Qdrant, which recorded 41 QPS under identical conditions. This isn't just a marginal gain, we are talking about a 10x throughput advantage. In the past, we accepted the specialized engine overhead because we thought Postgres couldn't scale. But with the integration of DISCAN-inspired algorithms, Postgres now processes massive vector workloads while keeping your data ACID compliant. Most teams are shocked to find that the old reliable database is now the speed king of the AI era. But speed alone isn't the whole story, it's about how that speed feels to the end user. In production, your users don't care about the average. They care about the P95 latency, the slowest 5% of requests that make an app feel broken. When benchmarking against Pinecone's serverless architecture at the 50 million scale, pgvectorscale demonstrated a 28-fold reduction in P95 latency. Why such a massive gap? Specialized SaaS providers often suffer from network jitter, multi-tenant scheduling delays, and the inherent cold start problems of serverless scaling. By keeping your vectors inside Postgres, you eliminate the high cost of moving data across the network to a separate silo. You're querying data where it lives, on local NVMe or optimized EBS volumes, without the noisy neighbor effect common in shared cloud environments. This predictable performance is what allows developers to build RAG systems that respond instantly. But does this raw speed compromise the quality of the search results? There is a persistent myth that Postgres only offers basic vector search compromises on accuracy for the sake of convenience. The 2026 benchmarks prove this is false. Even at the 50 million scale, pgvector and pgvectorscale maintain a recall accuracy of over 99%. Recall measures how often the database finds the true nearest neighbors compared to a brute force search. Specialized engines like Pinecone or Weaviate no longer hold a quality advantage. By leveraging the same SW and DISCAN logic used by the industry giants, but integrating it directly into the Postgres buffer cache, we get the precision of a specialist with the stability of a generalist. You don't have to choose between a database that works and a search engine that is accurate. Postgres is now both. Now that the performance argument is settled, let's look at the impact on your company's bank account. Infrastructure cost is where specialized vector databases often become a liability. When you use a managed SaaS like Pinecone, you aren't just paying for storage, you're paying a significant premium for their proprietary orchestration and management. In a 2026 TCO analysis, Moving 50 million vectors from a specialized SaaS to a self-hosted or managed Postgres instance resulted in a 75% reduction in total costs. This includes the hidden costs like data transfer fees, which skyrocket when your application server in AWS East 1 has to constantly fetch vector results from a different provider's cloud. By consolidating your vectors into your existing Postgres cluster, you leverage existing reserved instances and storage commitments. It's the difference between a sustainable AI project and one that gets shut down due to runaway cloud bills. But the financial cost is only half. The burden management complexity is the other half. Every new database engine you add to your stack is a new way for your system to fail at 3 a.m. If you run a specialized vector DB alongside Postgres, you now have 2 backup policies to manage, 2 monitoring stacks with different Prometheus exporters, and 2 security models for IAM and encryption. The synchronization tax is real. I've seen teams lose weeks of productivity debugging why a vector index is out of sync with the main relational database. When a user updates their profile in Postgres, that change must be propagated to the vector DB instantly, or your search results become stale. This creates a distributed systems nightmare. By using pgvector, your vectors are backed up during your standard database snapshots and protected by the same security audits you already trust. It's one less thing to monitor, which means more time for building features. But wait until you see how this simplicity transforms your actual code. The ultimate win for Postgres isn't just performance or cost, it's developer productivity through SQL. In a split architecture, you perform a vector search in one DB, get a list of IDs, then run a second where-in query in Postgres to get the metadata. This N+1 pattern is brittle and slow. With Postgres, you can join your vector similarity results with relational tables in a single atomic statement. You can filter by customer tier, check if a product is in stock, and perform a semantic search all in one go. There is no glue code to write and no stale metadata to worry about. This is why Postgres won the 2026 shift. It transformed vector search from a complex infrastructure problem into a simple feature of the database you already know. Now, if Postgres is the clear winner, how do we choose between the classic pgvector and the high-octane pgvectorscale? That's the critical decision we tackle next. In the world of vector search, the index you choose is the single most critical factor for performance. Standard pgvector offers 2 primary choices, IVFFlat and HNSW. IVFFlat works by clustering vectors, which makes it fast to build but requires a training step and often suffers from lower recall as your dataset grows. On the other hand, HSW creates a multi-layered graph structure. In practice, HNSW is the gold standard for search speed and accuracy in 2026, but it comes with a heavy price, high memory consumption, and long index build times. Many developers realize too late that their HNSW index has outgrown their available RAM, causing the database to swap to disk and performance to plummet. Understanding the build time versus search speed trade-off is your first step in avoiding an architectural dead end. But what happens when your index grows so large that it simply cannot fit in RAM anymore? This is where pgvectorscale enters the frame, specifically with its implementation of the diskn algorithm. Unlike traditional HSW, which lives primarily in RAM, diskn is designed from the ground up for SSD resident indices. It uses a compressed graph approach that allows the index to stay on disk while maintaining search speeds that rival in-memory structures. In my experience, when you cross the 10 million vector threshold, the cost of RAM for HNSW becomes prohibitive. pgvectorscale solves this by optimizing for high-speed NVMe drives, ensuring that the distance between nodes in the graph is traversed with minimal IOPS. It's a game-changer for teams running massive RAG applications on a budget. You no longer need to vertically scale your Postgres instance to hundreds of gigabytes of RAM just to support semantic search. The secret to this performance lies in how data streams through the buffer pool. Let's look at the streaming B tree next. To bridge the gap between traditional relational storage and modern vector demands, pgvectorscale introduces the concept of the streaming B tree. Standard Postgres B trees are great for scalar data, but struggle with the high-dimensional access path patterns of vectors. The streaming tree optimizes how Postgres manages its buffer pool by prefetching and organizing vector data in a way that minimizes random disk reads. From a systems perspective, this reduces the I/O weight that typically kills database performance during high-concurrency vector searches. It treats the vector index not as a black box, but as a first-class citizen of the Postgres storage engine. This level of integration is why Postgres is winning. It leverages decades of buffer management logic and layers specialized streaming on top. Efficient storage is great, but how do we build these massive structures without taking the production database offline? Building an index on 100 million vectors can take days if not configured correctly, potentially locking your tables or exhausting system resources. To prevent this, modern Postgres setups utilize parallel index builds. By adjusting parameters like max parallel maintenance workers and increasing maintenance work mem, you can distribute the indexing workload across multiple CPU cores. In 2026, pgvector has matured to the point where it can handle these builds quite gracefully without blocking reads. However, the anti-pattern I often see is developers running a create index on a live production table without the concurrently keyword or failing to account for the temporary disk space required for the build. Always monitor your WL write-ahead log. Traffic during this process is building a massive AS and edgy index generates a significant amount of log data. Indexing is only half the battle. The real cost savings come from how we represent the vectors themselves through quantization. When you have millions of 1536-dimensional vectors, memory becomes your most expensive resource. Scalar quantization, specifically SQ8, is the first line of defense. It converts 32-bit floating point numbers into 8-bit integers. This simple mathematical shift reduces your memory footprint by 4x. While you might worry about losing accuracy, the reality in RAG systems is that the semantic meaning is preserved well enough for the initial retrieval phase. You can store 4 times as many vectors in the same RAM, or reduce your cloud bill by 75%. In the real world, the precision loss from SQ8 is often less than 1%, which is a negligible trade-off for such massive hardware savings. If 4x isn't enough, we need to look at product quantization, the heavy hitter of compression techniques. Product quantization, or PQ, is a more sophisticated approach. Instead of just rounding numbers, it breaks each vector into smaller subvectors and replaces them with a centroid ID from a pre-calculated codebook. Think of it like a lossy image compression for vectors. You can achieve 10x or even 20x compression ratios. In pgvectorscale, PQ allows you to handle datasets that would normally require a massive distributed cluster on a single, well-optimized Postgres node. The trade-off here is more complex. The build time increases because you need to train the codebook, and the search latency slightly increases due to the decoding step. But for billion-scale datasets, PQ is often the only viable path. But there's an even faster way that relies on simple binary logic. Let's see how Postgres handles bits with binary quantization. Binary quantization is the extreme end of the spectrum. It turns every dimension to a single bill or 1 based on whether it's above or below a threshold. This allows the database to use the Hamming distance, which is calculated using ultrafast XOR and bit-counting CPU instructions. While the accuracy drop is significant, the speed is incredible. In Postgres, we use this as a coarse filter. You perform a lightning-fast search on the binary bits to get the top 1,000 candidates, and then perform a precise re-ranking on just those few. This oversampling and re-ranking pattern is how we achieve 2026 level performance, millisecond latency on massive scales. Implementing this in SQL is straightforward, as shown in the code here. Which one should you choose? Let's map out the final precision speed trade-off matrix to help you decide. To wrap up this deep dive, you must balance 3 pillars: recall, latency, and cost. If you have under 1 million vectors, just use standard HNSW with full precision. Postgres can handle it easily. If you have 1 to 50 million, switch to pgvectorscale with diskNN and scalar quantization to keep costs low. For anything beyond 100 million, product quantization or binary quantization with re-ranking becomes mandatory. Don't fall into the trap of over-engineering early. Start with the simplest Postgres setup and scale using these extensions as your data grows. The beauty of the Postgres ecosystem is that you can migrate between these strategies without changing your underlying infrastructure. Now that we've mastered the internal mechanics of Postgres, how does it stack up against dedicated titans like Pinecone or Qdrant? In the next chapter, we look at the ultimate decision matrix. Let's be real. Most of you considering Pinecone are doing it because you don't want to manage infrastructure, and that's a valid reason. Pinecone is the poster child for the serverless vector database movement. It's designed for teams that need to go from zero to production in hours without worrying about pods, nodes, or index tuning. Its primary advantage is the decoupling of storage and compute in its serverless tier, allowing you to pay for what you actually search. However, as an architect, I have to warn you about the black box tax. You lose granular control over the indexing process, and the costs can scale unpredictably as your request volume spikes. It's a trade-off between engineering speed and long-term cost efficiency. If your team is small and your budget is flexible, Pinecone is a strong contender. But what if you need more than just a managed black box? Next, we look at the engine built for high-performance filtering. When we talk about Qdrant, we're talking about pure Rust performance. Unlike general-purpose databases, Qdrant was built from the ground up to handle vector similarity search with complex filtering. The standout feature here is the payload filtering engine. In many RAG applications, you aren't just searching for vectors, you're searching for vectors where the category is electronics and the price is under $500. Qdrant handles these Boolean filters during the HNSW graph traversal, which is significantly faster than post-filtering. It offers incredible flexibility, allowing you to run it as a managed service, in a Docker container, or as a distributed cluster on Kubernetes. For developers who want low-level control over how their indices are built and partitioned, Qdrant is often the superior choice over Pinecone. But speed isn't everything. Sometimes how you model your data objects matters more. Weaviate approaches the vector problem from a data object perspective. If you come from a background of GraphQL or document stores, Weaviate will feel like home. It doesn't just store vectors, it stores objects with a rich schema, allowing for complex cross-references between data points. Its multi-tenancy support is also one of the most mature in the market, which is a massive deal breaker if you're building a B2B SaaS, where customer data isolation is mandatory. Weaviate's architecture allows it to store vectors on lightning-fast NVMe drives while keeping the index in memory, balancing performance and cost effectively. It's a schema-first database which forces better data discipline than the more flexible Qdrant or Pinecone. This brings us to a critical question. When does all this specialized power become unnecessary overhead compared to the database you already know and trust? To make a final decision between these specialized players in Postgres, you need a side-by-side view. Look at the filtering capabilities and dynamic metadata support. While Pinecone is great for simplicity, its metadata filtering was historically limited compared to Qdrant's rich payload types. Weave wins on developer experience with GraphQL but requires more memory management. Postgres, with pgvector, might look like the underdog in raw OPS, but it wins on consistency and the power of SQL. 2026, the gap is closing. Most specialized DBs are adding SQL-like interfaces, and Postgres is adding specialized vector hardware acceleration. The real differentiator now is how your team operates. Do you want to manage another distributed system, or do you want to leverage your existing DBA skills? The feature matrix is only half the story. The other half is the scale of your data. If your dataset is under 10 million vectors, stop looking at specialized databases. Seriously, I've seen so many teams over-engineer their stack by adding a dedicated vector DB when pgvector would have handled everything within their existing Postgres instance. Why? Because under 10 million vectors, the overhead of network latency between your app and a specialized SaaS often exceeds the search time within Postgres. Plus, you keep your ACID guarantees, you can perform joins between your metadata and vectors without moving data, and your backup strategy remains unified. For 99% of enterprise RAG projects, 10 million vectors cover all the documents, chunks, and embeddings they'll ever need. Postgres is the boring choice that works. But what happens when you cross that 10 million threshold and things start to slow down? Once you hit the 10 million to 100 million vector range, a standard pgvector HNSW index might start to strain your RAM. This is where pgvectorscale enters the room. By using the DISCAN algorithm, pgvectorscale allows you to store the majority of your index on SSDs while maintaining high search accuracy and speed. This mid-scale tier is the optimization phase. You don't necessarily need to migrate to Pinecone yet. You need to optimize your Postgres configuration. You'll want to look at your work mem settings and consider using the streaming features of DISCAN. At this scale, your indexing time becomes a bottleneck, so you'll start using parallel index builds. It's a sweet spot where you're still leveraging Postgres, but you're treating it like a specialized high-performance engine. But eventually, even the best-tuned single node hits a wall. Let's talk about the 100 million vector cliff. At 100 million vectors and beyond, you are in the extreme scale territory. Here, a single Postgres node, no matter how many NVMe drives you throw at it, will struggle with query latency and reindexing times. Now, you have two choices. Option A, shard your Postgres instance using Citus. This keeps your SQL ecosystem, but adds significant operational complexity in managing a distributed Postgres cluster. Option B, move to a dedicated distributed vector engine like Qdrant or Milvus. These are designed to be horizontally scalable by nature, handling sharding and replication of vector segments across dozens of nodes. At this scale, the vector database trap is trying to keep everything in a single instance for too long. If your business depends on searching 1 billion vectors with sub-100 ms latency, it's time to admit you need a specialized distributed system. The decision depends on whether your team is better at managing Postgres clusters or native vector clusters. So here is your definitive 2026 decision flowchart. Start with Postgres. If you are under 10 million vectors, stay there. If you're growing, add pgvectorscale. Only if you hit the 100 million mark or you have a specific requirement like Pinecone's serverless convenience or Qdrant's unique filtering needs should you look elsewhere. Don't let shiny object syndrome dictate your architecture. The most expensive part of your infrastructure isn't the AWS bill. It's the engineering hours spent syncing data between two different databases. Keep it simple until the scale forces you to do otherwise. In the next chapter, we're going to get even more practical. We'll look at battle stories, real-world migration failures, and successes where teams had to move from one of these to another, and the lessons they learned the hard way. Let's dive into the reality of migration. In the world of Postgres, everything is a row, and every update is technically a new insertion due to MVCCC. When you are dealing with vector embeddings of 1536 dimensions, an update isn't just a tiny change. It's a massive write operation. Many developers move to pgvector and are shocked when their storage usage triples in a week. This is bloat. If your auto-vacuum settings aren't aggressive enough, the HNSW index starts pointing to dead tuples, causing search latency to spike from 20 ms to 500 ms. You must monitor pgstat user tables and tune the vacuum scale factor specifically for these high-churn vector tables. Simply adding more disk space is a temporary fix that leads to a performance cliff. You need to understand how Postgres handles the life cycle of these large binary objects to survive in production. But bloat is just the tip of the iceberg. Wait until you see what happens when you miscalculate your memory requirements. The most common performance killer I see in the field is under-provisioning RAM. Vector search using HNSW is fundamentally a memory-bound operation. The entire HNSW graph, or at least the top layers and the most frequently accessed nodes, must reside in the OS cache or shared buffers to maintain millisecond latency. If you have 10 million vectors with 1536 dimensions using 4-byte floats, that is roughly 60 GB of raw data, plus index overhead. If you try to run this on a 16 GB RAM instance, Postgres will be forced to swap pages from the SSD constantly. In this scenario, your IOPS will max out, and search quality won't matter because the latency will be intolerable. You must calculate your working set size carefully. Always aim for a RAM size that covers at least 70% of your total index size plus the active relational data. The difference between hitting the RAM cache and hitting an NVMe drive is orders of magnitude in the vector world. We've talked about performance, but what about data integrity during a crash? The safety net is more fragile than you think in specialized databases. Let's talk about a war story involving partial update failures. In many specialized vector databases, the metadata and the vector embeddings are handled by different underlying storage engines or even different nodes. If your application attempts to update a user's subscription status and their preference vector at the same time, a network hiccup can lead to a ghost vector where the vector is updated, but the metadata rollback fails, or vice versa. This lack of ACID compliance forces you to write complex cleanup scripts or reconciliation workers. With pgvector, because it's part of the Postgres core transaction, the update is atomic. If the transaction fails, the write-ahead log, ensures that neither the metadata nor the vector change is committed. This safety is why many financial services teams choose Postgres despite the higher management overhead compared to serverless specialized options. Knowing these pitfalls, you might decide to consolidate your stack. But how do you actually move millions of vectors without downtime? Migrating 50 million vectors from a service like Pinecone back to your own Postgres instance isn't something you do with a simple export-import script. You need a zero downtime migration bridge. The first step is implementing dual writing. Your application starts writing all new vectors to both the old and new databases. Next, you run a background backfiller. This worker reads historical data from the old DB in chunks and upserts it into Postgres. The trick here is handling the overlap period where the backfiller might try to write an old version of a record that was already updated via the new dual write logic. By using on-conflict do-ubi data in SQL, you can ensure that the most recent data always wins. Once the lag between the two systems hits zero, you flip the read traffic. Getting the vectors over is easy, but mapping the unstructured metadata of a specialized DB into a clean relational schema is where the real work begins. When moving from a specialized DB, you often inherit a messy, flat metadata schema. Don't fall into the trap of just creating one giant table with a JSON column for everything. While JSON is great for flexibility, it's terrible for join performance if you have millions of rows. The proper architectural approach is to normalize high cardinality fields. If you frequently filter by organization, id, or user role, these should be dedicated columns with standard B-tree indexes. This allows Postgres to use a bitmap heap scan to combine the results of a vector search and a traditional relational filter efficiently. For the remaining long-tail metadata, JSON is perfectly fine. This hybrid schema is exactly why we moved to Postgres. It allows your vector data to participate in the complex business logic of your entire ecosystem. The code looks clean, but how do we prove to the stakeholders that the new search is actually as good as the old one? The final stage of any migration is validation, and in vector search, that means measuring recall drift. Because HSW is an approximate algorithm, the results from Pinecone might be 98% accurate compared to a brute force search, and pgvector might be 97% accurate with different parameters. You must run A/B tests on a representative query set, calculate the Jaccard similarity of the top K results between the old and new systems. If you see a major drop in similarity, you need to tune your NS of search parameter in Postgres. Also, perform load testing. A common mistake is assuming Postgres can handle the same QPS as a specialized DB on the same hardware. You need to verify that under peak load, your P99 latency stays within acceptable limits while the background vacuum process is running. This migration is just the beginning of your journey. In the final chapter, we'll look at the long-term best practices to keep your vector engine purring. When you're designing your data architecture in 2026, the most dangerous move isn't picking the wrong technology, it's picking too much technology. I've seen countless teams rush into specialized vector databases like Pinecone or Qdrant for datasets that barely hit 1 million rows. That's an anti-pattern. Your team is already running Postgres. Sticking with pgvector is your do number one. It keeps your relational data and vectors in one ACD-compliant transaction. Don't let benchmarks from 2023 fool you. With the Discan-inspired algorithms in pgvectorscale, Postgres now handles massive scales with ease. Another critical don't is ignoring the maintenance cost of a separate data silo. Every new database is a new security perimeter, a new backup strategy, and a new point of failure. Ask yourself, is the efficiency gain worth the 50 hours of extra DevOps work per month? Usually, the answer is no. This checklist should be your guide during the initial design phase. But how do we know exactly when the limits of Postgres are reached? I'll show you the hard ceiling in the final wrap-up. To wrap things up, let's look at your implementation roadmap. Start with Postgres. It's the safest, most cost-effective entry point. You only need to consider a move when you hit the hard ceiling. In 2026, that ceiling is roughly 100 million vectors, or when you require hyper-specialized features like native multi-tenancy at the physical layer or complex hybrid search that Postgres struggles to optimize. For most of you, the operational simplicity of keeping everything in one place will result in faster shipping times and fewer production incidents. Remember, the vector database trap is thinking you need a new engine just because your data has a new shape. Real engineering is about making the most of the tools you already have before adding complexity. This is the difference between a developer who follows hype and an architect who delivers value. So take these checklists back to your team and audit your current stack. This concludes our journey through the vector landscape. Stay tuned for our next series where we'll tackle the next big infrastructure hurdle, distributed transaction management in the era of AI agents.